Hello everyone. So this is the second video on tensor analysis in R3, and so last time I just introduced the idea of what a scalar vector and a tensor field means on R3, and I said that we will look into the definition of various differential operators for these kind of fields, first in the Cartesian setting and then in the context of generalized curvilinear coordinates. So this video will be about the study of Cartesian tensors. Okay, so we're going to study Cartesian coordinate systems. Systems on R3. So this is just what you're used to earlier, and I think this was also covered in class. And the idea is to define all the key differential notions like the covariant derivative, the gradient, the divergence, and the curl. Okay, these are operations that you would see repeatedly in the study of continuum mechanics, and it helps to have a clear understanding of how to derive these expressions for scalar, vector, and tensor fields. And what I'll do is I'll provide a unified perspective, a way to derive all these from one single idea. The idea is that of a directional derivative. Again, I will not go into the full theory behind what a directional derivative is and why that is fundamental and so on. We discussed some of it in the class in the context of the cathode differential. We introduced two different notions of derivatives. One was the Fréchet derivative, which is the stronger notion, and then we also looked at a weaker notion of derivative called the cathode differential. In the context of nonlinear maps between vector spaces. In many ways, this is just the generalization of that for fields on R3. Okay, good. So I'm going to first look at a case of a scalar field f from R3 to R. Okay, so remember that this is nothing but a scalar field, and we're going to look at the directional derivative of a scalar field. So let me draw a diagram to illustrate this. Suppose I have this is a standard axis, the Cartesian axis 1, 2, and 3, and then what f from R3 to R means is that given any point x in R3, I associate a number f of x at R3. Number isn't real number, okay, and I associate this for every single point in three-dimensional space. Now, what does it mean to say that f has a directional derivative? Notice that f in general varies. So suppose I choose a neighboring point x plus delta x. Okay. Let me put this x plus delta x1 because there are many neighboring points. So let me consider one particular neighboring point x plus delta x1. Now what happens as to f as I move from x to x1? X to x plus delta x1. How does f vary? Okay, and likewise I can look at some other point x plus delta x2 and ask the question how f varies as I move from x to x plus delta x2, and so on. I can ask this question for every single direction. So what this directional derivative tells me is that if I give you a general direction, okay, and by direction I mean a particular vector h, if I move along h by a very small distance, how does f change? What is the rate at which f changes in the direction h? Okay, and the definition is very simple, okay, and it naturally follows from the description I just gave. So any change, if I want to look at a neighboring point to x in the direction of h, I can think of it as simply some constant s. S is a real number times h. Okay, Now what does this tell me? And so for instance, I can move along this direction to a point x plus s times h, and s, you can think of h as a unit vector and s as the distance, as a scaling factor by which the unit vector is multiplied. So when s is equal to 0, I'm at the point x. When s equals 1, I'm at the point x plus h. When s equals 2, I'm at x plus 2h, and so on. So I can recover the entire line passing through the point x in the direction h by this process as I vary h. Now the important distinction here, important point to keep in mind is that s is positive. Okay, I'm only interested in the positive direction. Okay, I'm looking at what happens to f as it moves along the positive h direction. Notice that f could have a very different behavior on minus h directions. Okay, the simplest way to see this is as a one-dimensional function. Suppose I have a function here at this at a point x, so I can have a function that goes like this. Okay, let's say just a function. Now this function has a very strong gradient in this direction, whereas if I move towards this side, and it has a different gradient. Okay, I mean of course if it's a what do you say, if it is a smooth function, of course the gradient has to be the same at a given point because it's unique. But so the distinction doesn't really matter. But so what this diagram really means is that if I look at a point close to x on the right hand side, the gradient is very different from the gradient on the left hand side. The gradient varies differently. Okay? But since this notion can be extended to non-smooth functions also, I will have this restriction that s is greater than 0. I mean, it's if that is confusing to you, you can as well assume s to be some arbitrary real number. It doesn't really matter as long as you're dealing with smooth functions, which is what we're doing in this course anyway. Okay, good. So what is the directional derivative according to this definition? So it tells me that if I look at the variation of let me write it over here so that it becomes clear. So s is implicitly assumed to be positive, and of course you can have it to be negative also in this case because we're dealing with smooth functions. Okay, good. Now the idea behind a directional derivative is that we move x along the direction h by a small amount and compare it to the value at x. Okay, and we are looking at this derivative, this limit rather, okay, as s tends to 0. Sorry, the limit as s tends to 0 of this particular ratio. And what does this tell you? This tells you the rate at which f changes along the direction h, very simply. And this can, remember that this can be written as d over ds, which is the rate at which f changes at s equal to 0, okay, of f of x plus sh. It's just a rewriting of the derivative. That's exactly how the derivative is defined. Okay, and this is called as the directional derivative of f. It's called the directional derivative of f at x along h. Okay, that's important to understand. And in this case, it's also given a special symbol. I'll use this symbol, the gradient, the Nambla symbol of f along the direction h at x. Okay, and when written like this, it's also called as the covariant derivative of f. Okay, again at x along the direction h and 1. So these are identical notions. I will define the covariant derivative in terms of the directional derivative. Okay? The idea of a covariant derivative is that it generalizes the notion of a directional derivative for vector and tensor fields. But I'm going to adopt a very simple definition to start with. We'll look at the Cartesian setting, in which case these are identical. Okay, so that's all good. So now you know how to compute the directional derivative. So let's do that. Suppose I'm given a smooth scalar field what is the directional derivative of f along h at the point x. Remember that this is defined as the derivative at s equal to 0 of f of x plus sh. Now in this expression, what is implicitly understood is that x is a constant, h is also a constant, constants and constant vectors, and s is the only thing that varies. Okay, and remember s is a real number, so this entire thing is a function of one real variable. So f of x plus sh is basically a function which takes a real number and gives me back a real number. So in particular, I can take the derivative like this. So let's write this out in full to see what that means. So this is nothing but the derivative at s equal to 0 of f, and remember x is just a shorthand for a tuple of real numbers. Okay, so it's going to be x1 plus sh1, x2 plus sh2, x3 plus sh3. Okay, and now you can apply the chain rule of differentiation. So it's going to be the derivative of f with respect to the first variable multiplied by the derivative of the argument, the first argument with respect to s, plus the derivative of f with respect to the second variable, and so on. Okay, that's the standard chain rule. So it's going to be I'll write it as a sum over I going from 1 to 3 of the partial derivative of f with respect to x1 at the point x1, x2, x3 multiplied by h1, which is nothing but if I take the derivative of x1 plus sh1 with respect to s, I get x1, and when you evaluate it at s equal to 0, h1, and when you evaluate it at s equal to 0, you again get h1 times h1. That's the multiplication of real numbers. Again, this holds true for every I, so this is the equation. For this symbol x is actually not a very nice symbol mathematically speaking, right? I mean, if I write f as a function of y, then you should write partial of f by partial f yi, and so on. So a much neater notation is to represent it as partial I f. Okay, with the idea that if I is 1, it means that I take the derivative with respect to the first variable, partial derivative. Partial to f is the partial derivative of f with respect to the second variable, and so on. Okay? So this allows us to write it in a much neater fashion as the ith partial derivative of f at the point x times hi. Okay, that's the covariant derivative of f along h at x. So this is the equation that we want to derive. Okay, good. Now, once we have the covariant derivative of f, we can define the gradient as follows. Okay, I'm going to define a new function called the gradient of f at x. Okay, and this is defined as follows. If it turns out that I can write if I can write the covariant derivative of f at the along the direction h at x as the inner product of sum v of x and h. Remember, h is just a constant vector. Okay, if I can write it like this, then v is called the gradient of f. Gradient of f at x. Okay, and we will use the symbol grad f of x, and people also use the symbol gradient of f at x. Okay, in general, you can use either of these symbols, it doesn't matter, but in continuum mechanics, as we saw in the class, we will use two different versions of the gradient, one with respect to the current placement and one with respect to the initial placement. And so this symbol, which is much cleaner, becomes non-trivial to apply, but whereas this is much more amenable to manipulations, because you can write capital GRAD and so on. Okay, so which one you use here is a matter of personal choice. Okay? And since we are in the business of continuum mechanics, I'll stick to the GRAD f of x notation, but I'll also mention the other nabla based notation when it's required. Okay, so what this definition tells us in particular is that we have the covariant derivative of f at x along the direction is, if the gradient exists, can be written as the gradient of f at x dot h, or equivalently it's going to be it's written like this. Okay, so how you write it is just a matter of perspective. Good. Now, can we derive the expression for the gradient based on this expression? We derived the expression for the covariant derivative. Can we express the gradient from that directly? It turns out it's very simple, because you notice that I can write the covariant derivative of f at x, which is nothing but the summation over I of partial f at x hi. So I can write this as the inner product of or ei and hj ej. Why is that? Notice that these are all it's a linear combination of the basis vectors ei and ej, so you can multiply them, so you will have so this let me write it in different color. So this essentially is summation partial I f at x hj ei dot aj, but this is nothing but delta ij, so you can replace I with j and j with I, so it just becomes summation partial I f of x hi. Okay, which is exactly what you have here. So that justifies the way of writing it like this. Okay, that's very simple. Good. Now notice that this is of the form of the grade of the inner product of this quantity, and this is nothing but h. That's exactly the definition of the coordinate representation of h. Okay, so the component form of h rather, basis representation. So this immediately tells us that the gradient of f at x, or equivalently grad f at x, equals summation partial I f x ei. Okay, that's the equation. So notice that if I take f as a scalar field, then the gradient of f at any point x is actually a vector field. Okay, that's important to keep in mind, because the order of the thing increases by 1. A scalar field, remember, is a tensor field of order 0. The gradient is a vector field, which is a tensor field of order 1. So the order of the vector field increases by 1. We will see the general case soon. Okay. Now, of course, in the context of a scalar field, that is essentially all we need to know about the directional derivative, and this is something that you knew earlier also. Now let us see how this generalizes to the case of a vector field. Okay, suppose I have a vector field v from R3 to R3. Again, notice that I'm using the simplified representation in the sense that v is technically a function from R3 to the tangent bundle of R3, but I'm making the standard approximation that I mentioned in the previous video. Okay. Now, so the question is, what is the directional derivative of f? So what is the directional derivative of v at x along h? So what does this mean? What does this question even mean? Okay. Again, let's go back to the simple diagram. So this is our three-dimensional Euclidean space R3, 1, 2, and 3. Now suppose I take an arbitrary point x. Here, let's say I have a vector v. Good, but that's the vector field. So it's technically written as v of x. Okay, that's the vector field at the point x. Now the question is, what happens if I move along some direction h? So let's say I move to this point, some x plus sh. Okay. Now that's at that point the vector field could have some other value. Okay? It could have some other v of x plus sh. Right. So what the directional derivative tells me is, can I compare the vectors at different points and tell me how the vector field changes. And now comes an important simplification that R3 affords. Notice that v of x is actually an element of the tangent space to R3 at the point x, whereas v of x plus sh is an element of the tangent space to R3 at the point x plus sh. Okay, now these are two different spaces, two different vector spaces. Okay, so you cannot compare vectors in general between two different vector spaces. That doesn't make any sense. However, in the case of R3, which is a flat space, so this guy is flat. Okay, so what it means in particular is that this is isomorphic to R3 and this is also isomorphic to R3, so you can actually compare in this case. So the treatment becomes a lot simpler in the context of Euclidean spaces because of the fact that Euclidean spaces are flat. Let's exploit that. We will not worry about, in the general case you need to worry about a manifold where you have to be much more careful about how you define the directional derivative, but we don't have to worry about that here. Okay, good. So how do you define the directional derivative of v at the point x along the direction h? So this is read as the covariant derivative of v of v at x along h. Okay, that's the basic idea. Good. Remember that this is nothing but the directional derivative. It's exactly the same thing. It's called as the covariant derivative here. So let's define this. So based on the definition, remember we are interested in seeing how v changes as we move along the direction h by a small distance. So this is nothing but, by definition, it's nothing but s, the derivative at s equal to 0 of v of x plus sh. Again, notice that we are implicitly using the fact that the Euclidean space is flat. Otherwise, you cannot take this derivative. Good. Now, once this is done, the rest is straightforward, because all you have to do is to express that v in terms of a coordinate system, and in this case we are using the Cartesian coordinates. So it's going to be vi of x plus sh ei. And remember, ei is a constant, so you can take the derivative inside the sum. So it's going to be a sum of the derivative at s equal to 0 of vi, and just to make it clear, I'll write this as x1 plus sh1, x2 plus sh2, x3 plus sh3 multiplied by ei. Okay, so this is the total expression for the covariant derivative of v along h. And now we have a straightforward application of the chain rule. So this can be written as summation of the jth partial derivative of vi at the point x multiplied by hj. Okay, remember that you first take the derivative with respect to some argument and then take the derivative of the argument with respect to s, which gives you the corresponding component of h. That's exactly what is happening here. So the j here pairs with the j here. Okay, that's important. ei. So that is the expression for the covariant derivative of v along h in the direction x. Now once we have this, remember that the gradient is defined as the quantity such that the inner product of the gradient with h should give you the covariant derivative. Okay, let's see if we can write this in a particular form. So notice that based on simple observation, right? So you see the gradient, the covariant derivative of I got this wrong, sorry. You see that the covariant derivative of v along h in the direction at the point x is nothing but, I can write hj ei as follows. I can write this as summation partial j vi x ei tensor product aj dot hk ek. Remember that if you expand this, this just becomes summation over summation of partial j vi of x hk, and then you have the ei tensor product ej dot ek. That's the thing, and this by definition is nothing but ei times ej dot ek. So you take the inner product of the last two quantities here, and then you scale it along ei. Okay, and this is nothing but delta jk. So you just replace k with j, and you recover this expression. Okay, that tells you that this identity is indeed true. Good. And notice now that this quantity here is nothing but h. So that immediately tells you that the quantity here is the gradient of v. Okay, so what we see is that the gradient of v at the point x is nothing but this expression. It's partial j vi of x ei tensor product ej. Again, you can also write this as nabla v at x. Okay, that's also a notation that is used in practice. Again, notice how v is a vector field, whereas gradient of v is a second order tensor field. Okay, so it's a so when you have a vector field v, you get the gradient is a tensor field of one order higher. So this is a tensor field of order 1. So gradient of v is a tensor field of order 2. That's exactly as per our definitions go. Our expectation goes. Good. Now I'm going to define a new operation called the divergence of v. Okay, this is a new operation I'm going to define, and it's defined simply as follows. In this case, the divergence of a vector field v of x is defined as the trace of the gradient of v at the point x. Okay, what does trace mean? Remember that if I have a second order tensor like this, like what I have here, then the trace essentially tells me that I sum up the elements along the diagonal. So in other words, I do a contraction of the two indices I and j. Okay, so in this case it yields a very simple equation. So it's going to be the trace of partial j vi ei tensor product ej, but ei and ej, the I and j indices are contracted, so that leaves us with this quantity partial I vi of x. So this is at x. Okay, that's it. So that's the definition of the divergence of v at x. So this is remember, this is a scalar field. Notice how the gradient is actually a tensor field of one order higher. The divergence of v, will turn out, is a tensor field of one order lower than v. Okay, so v is a vector field and divergence of v is a scalar field. And so for instance, if you, in a more colloquial parlance, this can be written as partial v1 by partial x1 plus partial v2 by partial x2 plus partial v3 by partial x3 and so on. Okay, and while on this, if you look at the gradient itself, okay, the gradient can be written in matrix form as follows. If I look at the matrix expression for the gradient of v at the point x, so this can be written as the partial derivative of v1 with respect to x1, the partial derivative of v1 with respect to x2, the partial derivative of v1 with respect to x3, and so on. Okay, this so I'll just fill this out. This is not difficult, but you should know where it comes from, and you should know that you don't have to memorize the expressions. It just follows naturally from the definitions. The only definition that you need to keep in mind are that of a directional derivative. Okay, everything else follows from that. Good. Okay, and finally I'm going to define one more quantity called as the curl of a vector field. Okay, so I'm going to define the curl of V, and again this quantity is defined only in R3, okay, not in a general context, but it's important. So the curl of a V is again a vector field. If V is a vector field, curl of V is also a vector field, and they define as follows: choose any W in R3. So it's any constant vector, constant vector W. Then I define the curl of V as follows. The curl of V, remember it's a vector field, so I can take the inner product with W. So this is a real number. Okay, so this is defined. This should be the divergence of the cross product of V and W at the point at X. Okay, so let me write that down properly. So it's going to be the divergence of V cross W at X. Again, so here V cross W at X is nothing but V at the point X cross W. Okay, remember that V is a vector field, so V of X is a vector, W is a vector again, so that you can take the cross product, which gives you back a vector, and you get a vector at each point X like this, and you take the divergence of that field. And that's not easy, that's not difficult to work out. So remember that if I take V cross W at the point X, this is nothing but V of X times W. So this can be written in terms of the alternating symbol as follows: Vj of X Wk. Okay, so remember that epsilon ijk is the alternating symbol, which is 1 if ijk is an even permutation of 1, 2, 3, minus 1 if it's an odd permutation, and it is 0 if any two indices repeat. Okay, that's the definition. Okay, this is the standard expression for the inner the vector field, and of course I should add an EI here because it's a vector field, and so you should mention the basis vectors also. Good. Now once you have this, then you can easily compute the divergence. Remember that earlier we computed this expression for the divergence of V. So what we did was, if V is a vector field, which is written as Vi of XEI. Okay, let me write it like this. Let me write it more legibly. Okay, so recall that the divergence of Vi EI is summation partial I Vi of X. Okay, that's the definition that we saw earlier. So what I'm going to do is I'm going to look at this entire thing. Okay, as the free index here is I, so let me call this as xi. So the divergence of V cross W at the point X is nothing but the divergence of the vector field xi at the point X. This is nothing but summation partial I xi I. Okay, so all I have to do is substitute this expression over here, and I immediately get this is nothing but a summation of partial I epsilon ijk Vj of X Wk. And again, notice that epsilon ijk is a constant, Wk is a constant, so this just simplifies to summation partial I Vj. Let me write the epsilon ijk first. Epsilon ijk partial I Vj Wk. Okay, good. Now that is not the end of the definition. So remember that we define the curl as the vector such that the inner product of curl V and W gives you this expression. And again, so this can be written as the inner product of this vector epsilon ijk partial I Vj ek dot sigma W L E L. Okay, it's very simple, because if you take the dot product, you have an ek dot el, which is a delta k l, and you replace the l with k and you recover this, and this is nothing but w. So by definition this has to be curl v. That's it. Okay, and so the curl of v, so we have obtained a nice expression for the curl of v. So we see that the curl of v at the point x is nothing but summation epsilon ijk partial v partial I partial j ek. And there's a nicer way of writing this. So remember that this is nothing but epsilon kij, because kij has the same parity as ijk, so the value does not change. And now I can replace, I can just relabel the indices. Okay, replace k with I, j with I with k, j with I, and k with I, and so on. So what this gives you is epsilon I j k partial j v k e I. Okay, I've just relabeled the indices, okay, because this is a much nicer expression to keep in mind. So this is the expression. Again, people write this as the del cross v of x. Okay, that's another symbol that is used in the literature. So the important thing to keep in mind is that j pairs with okay. So j here pairs with the j here, whereas the third index k is over here. Okay, and the first index here pairs with the first index here. Good. That's the definition of the curl of a vector field. Okay. Now notice how we have the general framework that we have adopted. So you first define the covariant derivative, and from that you compute the gradient, right? Because the covariant derivative is essentially a directional derivative, and if you insist that the directional derivative is linear in the direction, you get the gradient from that, and from the gradient you take the trace and you get the divergence, and you use the divergence to compute the curl. So you don't have to really memorize any of the equations. You can just derive them based on this recipe. It's a very, very simple recipe, but we will follow that in the context of a general tensor field also. Okay, so finally, before I close this video, I'll briefly outline how you can apply the same thing for a tensor field. Okay, suppose I have, let's finally look at tensor fields. And to keep the discussion simple, I will show the general definitions in the context of a tensor field of order k, but I'll work out the expressions only in the context of a second order vector field, a tensor field. Okay, because that it's much easier to follow the calculations. So suppose that tau is a tensor field of order k. So what this means is that the tau is of this particular form, which takes up a point x to a vector tau of x. Okay, this is a tensor field of order k. And what we want to do is to compute the covariant derivative of this tensor, and from that compute the gradient, and from that the divergence, and from that the curl. Okay, there are some slightly non-trivial aspects. And for all the illustrations, I will use a second order tensor field, okay, which I'll write as t from R3 to T2 of R3. Okay, so this is just for concrete calculations. So how would you first of all represent tau? At any point x, tau of x is nothing but tau I1 all the way up to ik x ei1 tensor product all the way up to ek. Okay. So this is the general expression in terms of the standard basis ei of R3. Now what we want to do is to compute the directional derivative of tau along the direction h. So notice again, what does tau mean? It means that if I look at the look at my standard R3, then at any point x, I associate a function tau of x. Not just any function, it's going to be a multilinear function which takes k vectors at x and spits out a real number. Okay, so it's a special kind of a multilinear function, which is a multilinear function. which takes k arguments. Good. Now let's compute the covariant derivative of tau. Again, the covariant derivative of tau along the direction h at the point x. Okay, so this is the covariant derivative. And again, the definition is exactly the same, because we are dealing with a simple Cartesian setting. There isn't really any difficulty in extending the basic idea. So all you have to do is, as usual, choose a direction h and move x along h and compare the values of tau at different neighboring points, and then take the derivative. That's it. Okay, very good. So let's do that. So by definition, the covariant derivative of tau along h is nothing but the derivative at s equal to 0 of tau of x plus sh, and this is where you substitute the fact that tau has a coordinate expansion. It's going to be eik of x, ei1 tensor product all the way up to eik. Okay, so notice that the tensor product basis is constant. It's the same for all x, so it does not depend on x. And the first this should be x plus sh. So this is at x plus sh. Okay, now this quantity depends on s, so you just take the standard partial derivatives. You follow the chain rule of differentiation, so it's going to be sum of the partial derivative of tau I1 all the way up to ik. I'm just using let me use j. So let me use partial j ik at the point x times hj, again ei1 tensor product eik. So that's the expression for the covariant derivative of tau at the point x along the direction h. Good. Now from here the expression for the gradient is very simple. So this I can write this as the inner product of this tensor. So it's going to be tau I1 all the way up to ikx ei1 tensor product eik dot summation hk ek. I missed an extra term here, so it's going to be tensor product ej dot. Okay, so the derivation is very simple. So the inner product of by linearity, all the constants come out in the front, and so it's basically the inner product of this k plus 1 tensor product basis and this basis ek. And that of course means that you take the inner product of ej and ek, which gives you a delta jk. So this k gets replaced with j, and you recover this expression. Okay, so that's a very simple calculation. But notice that this quantity over here is nothing but h. So you've written the covariant derivative as some quantity dot h. So that immediately tells you that the gradient of tau at x is nothing but this expression. So it's going to be partial j of tau I1 all the way up to ik ei1 tensor product eik tensor product ej. Okay, and again notice that people use this term, this symbol sometimes. Okay, it's a great nabla tau x. Good. Now notice again that tau is a tensor field of order k. Okay, it's a tensor field of order k, and the gradient of tau is a tensor field of order k plus 1. The order increases by 1. Okay, this is just evident from the previous expression. And this neatly summarizes what we saw earlier. When tau, for instance, is a scalar field, it's a tensor field of order 0, and gradient of f is a vector field, which is a tensor field of order 1. When tau is a vector field, it's a tensor field of order 1, and gradient of V is a tensor field of order 2, which is what we saw earlier, and now we see the general trend. The gradient of a tensor field is a tensor field of one order higher. Okay, so let's look at a simple example when T was a second order tensor. So in that case, you can write it as summation Tij Ei tensor product Ej. And the reason for focusing on second order tensors is because the calculations are easier, and also because this is something that you will see repeatedly. For instance, the Cauchy stress tensor is a second order tensor, and the strain tensors, the Lagrangian strain tensor or the Eulerian strain tensors, those are also second order tensors, and so on. So that's quite common in continuum mechanics. So what we do now is, if you compute the gradient of T at a point x, again these are functions of x, okay, this immediately follows from the previous expression as summation of the partial derivative with respect to k, Tij Ei Ej Ek. Notice that this is a third order tensor. Okay, good. It's a very simple calculation. Now, so this was just an example. Okay, then, so now let's consider the divergence of tau. Earlier, when we studied vector fields, we defined the divergence as just the trace of the gradient. But of course, the trace of a gradient doesn't make much sense here, because the gradient itself is a tensor field of order k plus 1. So how do you define the gradient? Okay, and the idea is very simple. So let me first write the expression for gradient. So the divergence of tau at x. So let me write first the expression for the gradient. Let me write it in two steps here. I want to eventually define the divergence of tau in terms of the gradient. Okay, so in terms of the gradient of tau of x. So let me first write it like this. The gradient of tau is nothing but partial j tau I1 all the way up to ik ei1 tensor product all the way up to eik tensor product ej. Okay, now I can take the contraction of the last two indices only. Suppose I take these two indices and I contract these two indices. Okay, and that I represent it, remember I introduced this notation, the contraction of k and k plus 1. So what it means is I take the kth index here, which is nothing but this quantity, and the k plus 1th index which corresponds to this basis vectors, and I contract these two. Okay, so I'll write this in this point. So it's going to be c k plus 1 of gradient of tau. That's the definition of the divergence in the context of a general tensor field. Okay, now it's straightforward. All I have to do is I have to replace ik with j and do the summation, and the last ik will become j. So this is nothing but summation over of partial j tau I1 all the way up to ik minus 1, and then there's going to be a j times ei1 tensor product all the way up to eik minus 1. That's it. So remember that this is a tensor field of order k minus 1. Okay, and people also use this symbol del dot tau at x. Good. Now to actually see how this works, let's consider the example of the second order tensor that we had earlier. So t at x, so we have this second order tensor t of x, which is nothing but summation tij of x ei tensor product ej. Okay, now again following the definition of divergence, we see the divergence of t at the point x is nothing but the contraction of the second and third indices of the gradient of t, which we saw earlier as partial k tij ei tensor product ej tensor product ek. Okay, so of course the second and third indices have to be contracted, so that immediately tells you that this is nothing but summation over j tij ei. It's a vector field. That's the definition of if you want to write it in terms of the familiar partial derivative notation, so this is nothing but summation of partial tij of x over partial xj ei. Okay, so the second index is the one you take the summation over. Good. So that's the definition of divergence of tau. And there's an important point to be noticed here, which is that notice that I define C as the divergence as the k plus 1 contraction. But clearly that is not the only way to contract. I mean, if I even if I say that I fix this as one of the indices to contract, I have k options for the remaining contraction. Okay, so I can choose any one of these indices and I'll get a corresponding divergence. So the choice is clearly arbitrary. So why k and k plus 1, and why not say the first and k plus 1, and why not say the second k plus 1, and so on. So of course every single choice leads to one particular example of one particular case of a tensor field of order k minus 1. And all these are equally legitimate quantities, mathematical quantities. But it turns out that if you define it like this, in this particular manner, if you define it in terms of ck and ck plus 1, then this has use in many applications. Okay, so and that is why this is one reason why the index notation, for people who like the index notation, they argue that if I write a quantity like such as this, I immediately know which indices I contract. Whereas if I write something like in the coordinate independent form as divergence of tau, it's not very clear how you contract. Okay, so proponents of the index notation say that index notation is much more, even though it's cumbersome, it's at least clean because you know exactly what you're doing. But really, I mean, the choice is basically one of personal taste. I tend to like the coordinate independent notation. Okay, so this is or the component free notation, so that it is much cleaner conceptually. And whenever you have to work with a solid computation, you of course have to define exactly how you work with the indices. It's a small payoff, but then ultimately it depends on what you want to do. Very good. Okay, so that is the definition of the divergence of a tensor field. So let me finish with the expression for the curl of tau. Again, remember that the curl, in the context of a vector field, we computed the curl based on the divergence. We are going to follow a similar approach now. The idea is first choose any fixed w in R3 first, and then I have a recursive definition now. This is a very nice idea. You don't define the curl directly, but you define the curl in what is called as a recursive fashion. Recursive, maybe I'll write this recursive definition. Okay. And it's done as follows. If I take the inner product of w and curl of tau at the point x, this should be the same as the curl of w dot tau of x. Okay, it's a very simple equation. So notice that the first thing here is that this is a vector field. If tau is a vector field of order k, then curl of tau is also a vector field of order k, and we will see that very soon. And w of k is w of tau rather. Remember, this reduces the order of tau by 1. So this is a vector field of order k minus 1, and of course this is a vector here, so when you contract it, it reduces the order by 1. Okay, so that's it's very clean. Good. So let's see how it works. Again, the general definition is much more cumbersome to work with, so I'll work in the specific context of a second order tensor field. Okay, suppose as an example I consider t of x equals summation tij x ei. Okay, so how do we compute the curl of t right now? Okay, so if I choose any w, which is a constant vector in R3, then the definition tells me that the curl of w, the inner product of w and the curl of t, is the curl of w dot t at the point x. Okay, that's the definition. Again, you have to be careful about the order in which the inner product is taken. So if t is summation t I j e I tensor product e j, so in general w dot t is not the same as t dot w. Both are different vector fields. Okay, so w dot t is basically multiplying t from the left, so that's going to be summation of t I j w I e j, whereas t dot w is multiplication of t from the right, and that's going to give you summation t I j w j e I. Okay, so we have to be careful about the order of multiplication here. So what we have here on this side is nothing but the curl of summation t I j w I e j. Okay, so this is nothing but a vector field. So let me call this as, say, some xi j e j. Okay, so here the idea is that xi j is nothing but summation t I j w I. Okay, that's psi j. Now we know the expression for the curl of a vector field, and because we computed that earlier, in this case we computed the curl of a vector field here. So we'll use that expression exactly to write this down. Okay, so this is going to be summation of epsilon I j k partial j xi k e I. Good. Now what is xi k over here? So this tells you in particular that xi k is summation of t. I'm going to replace I with some other dummy index, so let's say a, and instead of j I have k, and it's going to be w a. Okay, so that's exactly rewriting the same thing. So so it's going to be epsilon I j k partial j t a k w a and then e I. Okay, good. Now we want to write this as w dot something. Okay, so I want to write this as the summation of w say w b e b dot something epsilon I j k partial j t a k, and of course instead of w a I want to have something like e a tensor product e I. Okay, the idea is that if you take the inner product, you have the inner product of eb dot ea times ei, but eb dot ea is delta ab. Okay, so b gets replaced with a, and you recover this expression. Okay, that's the basic idea. So that's the and again you see that this is nothing but w, so by definition this has to be equal to the curl of t, the curl of so that has to be equal to the okay, I'm messing around with this. Okay, the curl of t at the point x. Okay, so this tells you immediately that the expression for curl of t is nothing but the curl of t at the point x is nothing but summation of epsilon I j k partial j t a k e a tensor product e I. Okay, so now you can work out a similar expression for the curl of higher order tensor fields. The expressions become cumbersome, so I'm not going to bother about doing that in general. Okay, but I want to end with a simple note, which is that notice that in all these cases we have been following a simple recipe. The first is that you calculate the covariant derivative. Given any vector field or tensor field or scalar field, you compute the covariant derivative, and that allows you to compute the gradient. Okay, remember the gradient is nothing but the quantity, the tensor field, such that the inner product of the gradient and the direction over which you take along which you take the covariant derivative gives you back the covariant derivative. Okay, and once you have the gradient, you can define the divergence as basically the contraction of the last two indices of the gradient, and you can using the recursive definition you can define the curl of the corresponding quantity. So if I take a tensor field of order k, for instance, this is a tensor field, then the covariant derivative is also a derivative of as a tensor of order k. And the reason is very simply that if you look at the definition of the covariant derivative, what you're doing here is you're comparing the value of tau at two different points. So it's tau at x plus sh minus tau of x divided by s as s tends to 0. But that is nothing but the difference of two tensors is also a tensor of the same order because it's a linear space. Good. So this is also a tensor of order k. And when you take the gradient, and what you're doing is you're increasing the order by 1, so it's going to be k plus 1. What the divergence does is that you're taking the contraction of the last two indices, so it reduces the order of the gradient by 2. Or in other words, the order of the divergence is going to be k minus 1. It's 1 less than the order of the tensor field. And finally, the curl of a vector field, okay, it has the same order as your tensor field. Okay, the curl of a tensor field of order k is also a tensor field of order k, and that is also easily seen from this expression. Okay, if you look at the definition of the curl, you see that if tau is a tensor field of order k, then curl of tau also has to be a tensor field of order k, so that this expression is satisfied. Okay, good. So that completes the discussion of computing all the major quantities in Cartesian coordinates, and we saw that in class. I mean, we saw a lot of examples of this in class, but this provides a unified description. You don't have to really memorize any of the equations. All you need to know is the covariant derivative. Just understand the covariant derivative and understand how each of these quantities, the divergence, the gradient, and the curl, are defined with respect to the covariant derivative. And again, it's a nice recursive sequential definition. The covariant derivatives gives rise to the gradient, and the divergence is defined with respect to the gradient, and the curl is defined with respect to the divergence. Okay, so it's a very simple way to remember all these. There's no need to remember all these equations. There's a simple way to derive these equations. That's the point. Good. Now, what we'll do in the next lecture is, I'll stop this video here, but what we'll do in the next lecture is to extend this to general curvilinear coordinates. And the reason that gets interesting is that if you look at this expression here, where we define the covariant derivative, which is the starting point for everything, we have these basis vectors ei which are constant. But in the case of a general case, when you have a different set of basis vectors at each point x, these could be functions of x. So the derivative also has to extend to x, and you have to be careful about how you define those derivatives. Okay, and that leads to the more general expression for the covariant derivative, which is useful when you're dealing with curvilinear coordinates. So the next video will be on curvilinear, the same thing in terms of curvilinear coordinates. Okay?